the last thing that we're going to look at in this topic of combinatorics. The pigeonhole principle, basic idea, if you've got n+1 or more objects and you want to place them into n categories or n holes, then you know then there must be at least one that will contain two or more. Because if there's only n categories to place things in and you've got n+1 objects, well, there has to be one that has at least two in it. That's what it's basically saying. So let K, we're going to prove it, let K be the maximum number of objects that you can put into the n categories, the n holes, without having more than one object in a hole. We're going to prove it. So K is going to be the maximum number of objects we can put into the n categories, the n pigeonholes, without having more than one object in the hole. So basically we want to prove K is less than n+1. Because what I'm going to do here is a proof by contradiction. Assume K is greater than n+1. So proof by contradiction, I will assume the opposite to what I'm trying to prove. Assume K is greater than or equal to n+1. So the maximum number of objects would be n. Because we've got n holes and we said without putting more than one object in a hole. So the maximum number of objects I could have is n, one in each position. So therefore K has to be less than or equal to n. But there's your contradiction straight away. We want to prove that K is less than n+1. Let K be the maximum number of objects you can put in n holes. So we're assuming K is bigger than or equal to n+1. But we said the maximum number of objects would be n, because we said you can have no more than one object in a hole. So K has to be less than or equal to n. Well, hang on. It can't be greater than or equal to n+1 and be less than or equal to n. There's your contradiction. So thus, it can't be true that K is greater than or equal to n+1. Thus, K has to be less than n+1. So that's a simple little proof. So to generalise this, if K times n plus 1 or more objects are placed into n holes, n pigeonholes, n categories, call it what you will, then at least one of those holes must contain K plus 1 or more objects. Because if there's n holes, if I had K n objects, then each hole, you could distribute them evenly, each hole would have K. So if I've got Kn plus 1, then one of those must have at least K plus 1 objects. That's what that's basically saying. Now, let's look at them carefully. So 6 integers are selected from, well, we've got all the integers there going from 3 to 12. And we're going to get 6 of them. How many integers need to be selected to ensure that there are a pair of numbers that add up to 15? There are 5 possible pairs that will add up to 15 if you look at all those integers. You could have 3 and 12, you could have 4 and 11, 5 and 10, 6 and 9, 7 or 8. Okay? So n is equal to 5. There are 5 categories, if you like, 5 pigeonholes. So we're going to select an integer and put it in the appropriate pigeonhole. So if I pull out a 3, I'll put it in the first one. If I pull out an 8, I'll put it in the last one, and so on. So there's 5 I could put them in. So they are the pigeonholes, 5 of them. Now, let's say the pigeonhole principle tells us there's going to be 6 that need to be selected, because you've got 5 holes. 6 would be the objects that we're placing. So if I had just 5, right, as long as I've got 6, because there's 5 holes, at least one of those must have more than one object in it. That's what we're saying. So we need to ensure there's a pair of numbers. So we need to pull out 6 integers to ensure there's a pair of numbers that add up. All right, let's go to our second example. So we've got 50 points. We're going to place them in a 7 by 7 square. What's the maximum distance apart that the 2 closest points could be? That square I could divide up into 49 1-by-1 squares. Right, so 49, that's going to be the holes. So imagine you've got your 7-by-7 square, and we've basically made 49 spots we can put our points into. We've got 50 points, and the pigeonhole principle tells us that if there are 50 points, there must be a square that contains at least 2 points. Because I could put one in every square, I've got one left over. Oh, it's got to go in one of the holes. So therefore there must be at least one there. So the maximum distance, well, they would be the 2 closest points, the 2 that are in the same square. So the closest distance between the points would be the maximum. So the closest distance has to be a maximum. If you're placing it in the same square, then they would have to be at endpoints of the diagonal. That would give us the largest distance the 2 points could be apart. So a bit of Pythagoras then. D squared is 1 squared plus 1 squared, square root of 2. So the maximum distance that the closest pair of points could be is the square root of 2. Like, there might be another 2. I mean, these 2 here might be closer together. But that's not the question. The question is, what's the maximum distance apart 2 points could be? Okay, so it has to be the 2 closest points, which you would think have to be the 2. Well, it's not necessarily going to be the 2 that are in the same box, because they might be right next to each other in 2 adjoining boxes. But because we want the maximum distance that could be, I'll go, right, they're in the same box, and I'll put them on the endpoints of the diagonal. All right, we're going to prove that in a group of n people, there will always be at least 2 people with the same number of friends in that group. Okay? So you've got n people, there's going to be 2 people with the same number of friends. So it might be, you might have 2 people and the only people they know in the group is each other. So they both would have 1 friend. Or it might be you've got 4 people and 4 of them know 4, they know each other, but then there would be at least 2 with the same number, and so on and so on. The one thing for sure, it would be impossible for someone to have no friends and someone else to have n-1 friends. That would be impossible. Right? Because we are assuming that if I'm your friend, you're my friend, okay? So it's reciprocated. Because, okay, I'm the person that has n-1 friends. That means every other person is my friend. Therefore, it's impossible for someone to have no friends. So whether we choose the no friends to be impossible or the n-1 friends to be, one of them has to be impossible. I'm going to say we're a friendly group and there's no one there with no friends. Okay, so the possible number of friends a person could then have is 1, 2, 3, up to n-1 friends. In other words, there are n-1 different number of friends a person could have. They're our pigeonholes. So there's a category. We're now going to get every person and place them in a category. How many friends do you have? How many friends do you have? We're going to place them in a category. And we're going to show that, what is it we're trying to show? There will be at least 2 people that end up in the same category, have the same number of friends. Well, I could really just state it now, because if I've got n people and n-1 categories, there has to be at least one category that's got 2 people in it. So by the pigeonhole principle, there must be at least 2, but there's really no working out to do there. So I suppose the key to that question is the proving that part, that you could not have someone with no friends and someone with n-1 friends. It has to be one or the other, which then reduces the number of categories to n-1. 16 positive integers are written on the board. Now this time we want to know how many numbers will leave the same remainder when divided by 5. So it's just going to be 16 random positive integers. That's totally random. But at least how many of those numbers will leave the same remainder? Well, there's 5 possible remainders. No matter what number I put on the board, it's either going to be divisible, so remainder of 0, remainder 1, remainder 2, remainder 3. So there are 5 categories or pigeonholes, so we know n is 5. Kn plus 1 is 16, because that's how many objects, that's how many numbers we're writing on the board. So all we really now have to do is work out what k is, and we know we need k plus 1 numbers. Oh, it's just a bit of maths. 5k plus 1 is 16, k's 3. K plus 1 is 4, so that's the result we're looking for. So we know at least 4 of the numbers will leave the same remainder. We have a computer doing some work for us, generating random 3-letter words, and remember, in our terminologies, nonsense words are still words, so AAA is still a word. How many words do we need to generate to ensure there is a particular word that's been generated 8 times? Well, the possible words are going to be our pigeonholes, because when they generate the word, we're going to place it in a pigeonhole. And we want at least, how many we want? At least 8. We want 8 in a pigeonhole. So n, the number of holes, is going to be 17,576. K plus 1, because we want the result to be 8. So that tells me k is 7. So the number of objects we need to place is kn plus 1. Kn plus 1 works out to be 7 times 17,576 plus 1. We need to generate 123,033 words to ensure that a particular word has been generated 8 times. So the key is identifying what are the holes, what are the objects, what's the result, what is it we're trying to find? Is it the number of holes we're trying to find? Is it the result we're trying to find? Is it the number of objects we're trying to find? Alrighty, the pigeonhole principle.